So today's speaker is Dennis Schaart. Dennis heads the Medical Physics and Technology session at the Delft University of Technology, Delft in the Netherlands. He works in academia as well as the medical device industry, always at the intersections of physics, technology, and medicine. He started as an R&D physicist at Nucletron, now Electa, where he developed new devices for radiotherapy. He obtained his doctoral degree with highest honors in 2002, and after that, he joined Delft University. Bunch of other information. Now he leads the technology for oncology programs at the New Delft Health Initiative and serves as a member of the R&D program board of the Holland Proton Therapy Center. He has co-authored more than 150 peer-reviewed papers and is frequently invited speaker. That's why we have you here. Welcome. Thanks.
Thank you very much for the kind words, and especially thank you very much for inviting me here to this beautiful campus. It's wonderful to be here after about 10 years and to see what's happening in the program here at Nuclear Engineering. It's really impressive. I see a lot of great work on radiation detectors, a lot of work on fast radiation detectors. And I guess my mission for today is to bring you up to date with some of the work we've been doing in Delft, which is indeed very much in the field of medical physics. So I'm going to try to introduce some of those applications to you as well. Nevertheless, I think some of what I have to say today is more broadly applicable than just medical. Actually, my own interest is broader than medical, but I find myself in medical applications every day, so that will be the focus. Positron emission tomography is one form of medical imaging that uses nuclear principles. For starters, the source is a radionuclide emitting positrons. It's injected into the patient. The radioactivity distributes throughout the body, and of course, the positrons that are emitted will immediately annihilate with a normal electron in the body, emitting a pair of gamma photons in opposite directions. And if you're able to detect both of these photons, you can determine on which line between two detectors. So let's say you have a setup like this. I need to quickly find my. There we are. Where a patient is in a ring of detectors. If you have a pair of two detectors firing in coincidence at the same time, you know that the signal must have originated somewhere on that so-called line of response, or LOR. And then if you have some tens or hundreds of millions of these lines of response, you can mathematically reconstruct the radioactivity distribution inside the patient. And this is used frequently today in medical procedures. The classic example of an application is this one here. What we see here is actually a PET-CT image. So it is a PET image fused on a CT image. And the CT image is in gray, so that gives you the anatomy. And the PET image is superimposed in color. And yellow meaning a high radioactivity density. So what's going on here? This is a patient with a primary tumor in the pancreas, which is giving symptoms, and therefore the patient is in the hospital. And the question then is, has this tumor already metastasized? Has it spread to other locations in the body? And unfortunately for this patient, that appears to be the case. For example, you see here a metastasis that is probably in one of the ribs, but it's still very small. So it doesn't give any symptoms, but it's there, so it's need to be treated. So you can see how this is very important information for a physician who's trying to treat this patient. By the way, the big yellow blobs here, if you were wondering, those are just the kidneys already releasing the radio pharmaceutical. So that's totally normal. So the interpretation of these images is not always straightforward, but that's the job of the nuclear medicine physician. And these days, more and more AI, of course. And this task is basically called staging. So you're staging, you're trying to detect what stage the disease is in. In this case, unfortunately, it's already metastasized. There are many other applications And I don't have time to really go into that, but today PET is used for diagnosis, treatment monitoring, follow-up, research, you name it. The task that I just showed you is clearly a detection task where you're trying to find small lesions, essentially in a warm background. So you're looking for a small spot in a noisy background signal. So what you need is, of course, sufficient resolution, but you also need sufficient sensitivity to have a high SNR, a high signal-to-noise ratio in your image. Unfortunately, over the last 15 years, this factor has improved a lot in PET imaging because of the introduction of the time-of-flight principle. I just explained that in conventional PET, we are trying to find these lines of response, but the amount of imaging and the amount of information in one line of response is, of course, limited. If you think of an image as in this case, 2D array of pixels, then basically what you know with one line of response that there is a row of pixels, and the annihilation could have taken place in any of these pixels. Sorry, I tend to think in 3D these days, and it's voxels. And the likelihood in each of these pixels is equally large. So I like to compare this to a situation where you have about 100 politicians, for example, and they're all making a statement, and 99 of them are lying and only one is speaking the truth. Now, of course, in reality, the percentage of truthful politicians is probably lower than that, but it serves the example. Now, with time of flight, we are measuring the arrival time on the detector of the gamma photon on both sides. And since they are emitted at the same time, if you have the arrival times on two detectors, you can calculate the origin in principle. Now, the time resolution you need for that is not yet technologically achievable, but you can at least limit the range of pixels where the annihilation could have taken place to a smaller group of pixels. So now we have, for example, only 10 politicians, and 1 out of 10 is now speaking the truth. And 9 out of 10 is still making a false statement, but my signal-to-noise ratio has improved by a factor of 10. And that's the importance. What it means in practice is that in 2006, this is what a PET image would look like. So there's no CT here, this is just PET. This is the time where nuclear medicine was sometimes referred to as unclear medicine. And you can see there is a lot of noise, and there is also therefore a strong dependence on patient size, of course, because 2 gamma photons have to escape from the patient. Which means that they need to be not absorbed. And so especially in larger patients, the image quality was not very good. Now today, this looks very different. These are images taken in 2018 with one of the newest PET systems, state-of-the-art systems that's available now and actually already present in many hospitals. And you can clearly see the enormous improvement. And to a large part, this is, can actually make this one rotate. That's a fairly big patient, but you still see a lot of detail. And it's really phenomenal what has happened there. To a large extent because of time of flight. There are some other improvements as well, of course, but that's really the dominant one. So are we done yet? No, of course not. We always want more, faster, bigger, and so forth. But in particular, in what is sometimes called molecular imaging, because we are imaging the distribution of molecules in the body, what do we need? First of all, we need more tracers, more radiopharmaceuticals that we can use to target different processes in the body, study different diseases. Now, this is a radiochemical and biological topic that I'm not an expert on, so I will not go into it further, but I want to mention it because it's super important. It's the probe that we use, and the more probes you have, the more you can do. Of course, we always want to lower the radiation burden on the patient and the personnel. We want scan times to decrease. Scan times could take up to 30, 45 minutes 20 years ago. Nowadays, it's more like 10 minutes or so, or even shorter. But it would be great if it would be much shorter again. Flexibility, combination of PET with other modalities, and cost effectiveness. Cost is a big concern in healthcare, especially in our part of the world, where aging is taking place. So population, the average age is increasing, and it means more cancer, more heart disease, and so forth, and less people to take care of those sick people. So cost effectiveness is super important these days. What does that mean for the technology? To make these things happen, clearly we need even better system sensitivity. So being able to detect every gamma that is emitted from the patient. Of course, we always want better resolution. But if you have a better resolution in a 3D space, that means you have the number of voxels increases cubic compared to the resolution, to the power of 3. It's only useful if you can fill those voxels with counts. So resolution also implies sensitivity. Quantitative accuracy, we're actually doing a measurement here. We're not only taking pictures, we're measuring numbers, namely the number of becquerels per cubic centimeter in the body, because there is information in there. The absolute number tells you something about a process in the body. And of course, that means better SNR, and that means higher sensitivity. And finally, technology has to be compact, scalable, maintainable, all the usual requirements, and again, cost effective. But I hope I've been able to convince you that a very dominant requirement here on the technology side is to develop systems with even higher sensitivity. And that has brought me to formulate a figure of merit for the design of new PET detectors that looks like this. And we'll go into it one by one. But briefly, what we have here on the left is the detection efficiency per detector. So if I fire 100 gamma photons on the detector, how many of them do I actually detect? And then you have to take into account that I only have a line of response if I detect one photon and the other one. So this probability is squared in the equation. It's a multiplied probability. Then, of course, there is a geometry term. So that's basically the angular coverage of the detector ring around the patient. It should be as little gaps as possible. And then at the end, there's a term here, which is the equivalent patient diameter divided by the time resolution of the system, the time of flight resolution. And that's kind of a gain factor, a gain to the sensitivity that you get from time of flight. And the delta t is the coincidence resolving time, or the coincidence time resolution, as it is named interchangeably. And finally, you can divide all of that by the cost of the system. And you kind of, what you have here is an effective sensitivity or a unit cost, or dollar, if you want. And it's clear from this that better time of flight resolution increases this figure of merit. So we need even better time of flight. Faster is better. So we need to understand what makes a detector fast. And that is not so trivial, because if you go through the sequence of processes that make a signal happen if a gamma photon hits the detector, there's quite a lot going on in there. The gamma photon has to interact with the scintillator. The scintillator then produces a certain number of light in a certain amount of time with a certain pulse shape. That's being converted to, or actually there is first optical transport taking place in the crystal to the photosensor. I should not forget about this. This optical transfer is typically not 100% efficient. There is a spread on the transfer times of the individual photons, depending on the position of interaction. And then when the optical photons hit the photosensor, that's where your electronic signal is being made. Again, not all of the photons are actually detected. That's the photo detection efficiency of your sensor. Each photon is detected with a certain time resolution. That's the single photon time resolution, or the SPTR. And it can be effects such as dark hounds, crosstalk, and all the other undesired things that you can have in any electronic system. Now, of course, there's the readout electronics, where again, you need to worry about noise, you need to worry about bandwidth, impulse response, and so forth. So it's quite a chain of events. And if you want to improve something, you should understand how this works, because there's a lot of knobs to turn, and some of them make sense and others don't. Where do you put your effort, so to say? And of course, there is also the potential trap that you improve something with your left hand, and that has the effect that you deteriorate something on the other side, and the net effect is zero or even negative. So let's look at this a little bit more deeply. The first step is the conversion in the scintillator. So you need to understand what a scintillation pulse looks like. It is a finite number of optical photons being emitted in a finite number of time. The number varies per scintillator, and we express it typically in how many photons are emitted per unit or kilo electron volt, for example, of deposited gamma ray energy. And then we define an emission function, which is, you could simply say pulse shape, but emission function is a better term because it's actually probability density function. The likelihood of photons to be emitted given a certain T0, which is when the gamma photon interacts with the material, as a function of time. And for simple materials, this looks like an exponential, but typically with a finite rise time, so we can often approximate it as a dual exponential function. Can be more complicated like this, but for the purpose of this lecture, let's limit ourselves to the dual exponential scintillators, which have a rise time or rise time constant and a decay time constant. This is a measurement of an often used material, L-isocerium. And keep in mind that this is an expectation value, what you see here. This is a probability density function, I should say. Because the number of photons is finite and every pulse therefore has a certain noise on it as well, Poisson noise. Then, in terms of photosensing, you can use photomultiplier tubes, of course, as we used to do in the past, but any PET scanner today uses silicon photomultipliers, which is the technology that has enabled great improvement in time of flight over the past 15 years. An SIPM is basically an array of SPADs, single photon avalanche diodes, also known as Geiger mode avalanche diodes. So they're basically APDs that are overbiased above the breakdown voltage with a quenching resistor in series. So when an optical photon ignites an avalanche, the diode will actually break down, but it's a quenched process, so you will have a quenched circle that generates typically the order of 10 to the 5th or 10 to the 2nd or so electrons for every photon detected. And then you put many of these in parallel and you have a photon-counting. PDE can be high. We have devices with a photo detection efficiency of 65% these days, much higher than you can have with any PMT. And also the single photon time resolution can be extremely good. Less than 50 picoseconds is possible these days. And these are two very important numbers when it comes to timing. And these are also the numbers where SIPMs outperform conventional PMTs today. But we are not there yet, because in order to stop a gamma ray, you need a pretty thick chunk of scintillator, typically some centimeters in thickness. And if you imagine that here on the left-hand side, this is a so-called PET detector pixel, which might measure something like 3 or 4 millimeters across, that has a length of, for example, 20 millimeters or 30 millimeters. Excuse me for using metric, but I'm used to it as a European. What can happen is, if a gamma photon interacts in the bottom of the crystal, for example, the light can travel towards the photosensor pretty fast. But if a gamma photon interacts in the top of such a crystal, then the light that is emitted isotropically kind of has to find its way all the way down to the photosensor. And you can see that the path lengths are varying, and they're also typically longer. So this causes a delay. And to make things worse, the speed of light in a crystal is typically less than in vacuum, because these materials tend to have a very high index of refraction. in the order of 2 or so. So by approximation, every light photon actually travels at only half the speed of the gamma photon. So that worsens the delay. And so what I have now is an additional delay that depends on the distance of interaction, on the depth of interaction. And the depth of interaction is a stochastic parameter. It's different for every event. So what that is a time blurring mechanism. This smears out my time steps on the time axis. And this has been actually very nicely measured a long time ago already. There are 2 famous scientists, at least in my field, from this lab, Bill Moses and Stephen Lorenzo, in a publication in 1999, where, oops, where is my pointer? They made a very clever setup with a point source in between 2 crystals, where one crystal was standing up, so they could irradiate it at just 1 depth by putting it in coincidence with another crystal. And they measured this delay as a function of the depth of interaction. And you can see that it is easily in the order of hundreds of picoseconds, which is exactly the sort of time resolution that we want to improve upon. So this is becoming a very, very important factor. To put this into perspective, the best commercial time-of-flight systems today have a time resolution of 200 picoseconds. So this blurring factor is kind of one of the dominant limits right now, and we need to improve on that. So there's this depth of interaction effect, and as I sort of indicated already, there is also the time spread of the optical photons in the crystal itself. They are emitted isotropically, so they take random paths towards the photosensor, and the path length can be a largely varying parameter, which we measured in Delft using a femtosecond laser, just putting very short pulses of light into a sample and seeing how that light escapes from the crystal using a streak camera. And you can see again that it can take hundreds of picoseconds before all the light has really escaped from the crystal, even if they all enter all at the same time. So optical effects are becoming very, very important, and this is a topic of intense research at the moment, how to deal with these effects. And I want to show you just one example from our own kitchen in Delft. I call it time resolution recovery these days, trying to recover the original time of interaction in spite of these blurring factors. And we do that with something that may appear very counterintuitive to you. An obvious approach would be to make the crystal very, very small, because then all of these effects would be very, very small. The disadvantage is I pay with detection efficiency. A thin crystal becomes almost transparent to my gamma ray photons, so I don't see them anymore. And remember that factor, detection efficiency, goes squared into my figure of merit. So thin crystals is not something I want to do, unless I stack many of them on top of each other. But then it becomes, complex and expensive. So what we have been doing is going completely the opposite direction. Let's use very large crystals, monolithic scintillators as we use it. Think of cubes like this, which measures 3 by 3 by 2 centimeters, for example. And we allow the light to spread freely through that scintillator. And we read out the light from at least one of its surfaces, can be more than one, using a pixelated light sensor, like an SIPM array. So that's a 2D array of SIPMs, and I get a light pattern. So what I measure, I sample actually the light distribution on one of the surfaces of the crystal. And then you will see that if I change the position of interaction, the shape of that light distribution also changes. And as a bonus, if I change the depth of interaction, my light distribution also changes. This is fairly intuitive, and it sounds logical to reconstruct the position of interaction from the measured light distribution using some sort of machine learning technology, for example. Once I have done that, I could talk about just that topic for an hour, but I want to go fast. Let's say we have developed methods to pinpoint the position of interaction with a precision in the order of a few millimeters. So that works really nicely. So I know where my gamma photons are interacting in this block of material. How about the timestamps? Each of these pixels in my light sensor also produces a timestamp. Let's say when the first photon hits such a pixel, I get a timestamp. Now, obviously, you would expect that the pixel that is closest to the position of interaction would, on average, receive the first photon and generate the first timestamp. And then a pixel that's located a little bit further away would be next to generate a timestamp, and so forth. If I go further and further away, the timestamp occurs later. And this is somewhat reflected in these curves that you see here, which is a repeated measurement. Given a fixed position of interaction, when do these timestamps occur for this blue pixel here? That's this curve. Or the pixel with the green arrow, that's this curve. And you see indeed that on average, the average value shifts with the distance. But you also see there is actually a distribution. And that's because a photon, the very first photon that's being launched, or actually the very first photon that reaches this pixel here, may not travel in a straight line. It may actually be reflected on other surfaces before it reaches that pixel. And then I end up somewhere in the tail of this distribution. And that's the randomness of the emission process. I'm launching, let's say, a few thousand of photons in random directions. And every time this pattern of timestamps on my sensor changes. But I can measure it. And if I can measure these probability densities, and I know the position of interaction, then I can do something like, as we did, a maximum likelihood algorithm that estimates the most likely timestamp or the most likely time of interaction given my timestamps and the position of interaction. And that works quite well. You see here an example where with a naive timestamping, just taking the first one, I get a time resolution in the order of 200, 230 picoseconds, whereas with this M-Light method, I can improve it to something like 160 picoseconds, which is of course much better. So I've removed some of this blur. And of course, as I discussed already this morning with Josh, these days you should probably replace maximum likelihood with machine learning in order to get a grant approved. But otherwise, the approach would be the same. Just one example, there's many other ways to implement this. It's very important that we do some research in this area. And then what's the ultimate? Where do we want to go with this? Well, this is a slide I've been showing in 2011 already at a scintillator conference, where I sort of reasoned that the spatial resolution in PET is typically in the order of a few millimeters. So in order to get the same resolution on the line of response, you should have a time resolution in the order of about 10 picoseconds. At that time, my prediction was that that might not be possible because of physical limits on scintillators. And unfortunately, today, we still haven't reached this number. So up until today, I'm right in my prediction, but I hope to be proven wrong, of course. And some people are getting closer and closer. This is just a more or less random example from Stefan Gundacher, who is at that time was located at CERN, performing experiments with tiny crystals, excellent SIPMs, and lots of expensive readout electronics. He, at the time, he's improved it already in the meantime, but he achieved something like 60 picoseconds or so with a conventional PET scintillation material. So that's pretty good. And now this is a slide I've been showing for quite a while already, and this statement, which is here in red, always used to be on it, that what is the value of an experiment like this? Well, it shows that something like 60 picoseconds is physically possible, that's nice, but the approach is not very scalable to a full PET system. And that is true for the experiments that he did. This type of electronics consumes so much power per channel that if you would implement it in a PET scanner, it would become not only very expensive, but would also be very difficult to deal with all the power dissipation. Then, of course, when you say these things often enough, sometimes younger researchers like Josh try to be clever and try to prove you wrong, right? So they're now developing approaches to actually make this possible, but with much reduced power consumption. It looks like he's really getting there. So this is one of the nice things about science, that you can predict all kinds of things, but there will always be the young, brilliant scientists who will prove you wrong. And that's actually a very good thing. Another example using Cherenkov radiators, I don't want to go into it too much, but this is a Japanese group that even brought it down to about 30 picoseconds or so with a different approach. What I do want to point out though is that in this experiment, they did very strong event selection. In Cherenkov emitters, the number of Cherenkov photons emitted varies greatly from event to event. So in order to get this number, they had to select only the events in which they had the highest number of Cherenkov photons detected, which amounts to only a few percent of all the events. So what do you get? Very high timing. That was the linear factor at the end of my equation, at the expense of a 100-fold or so decrease in sensitivity, which goes quadratic in my equation. So the net gain of this is negative. And that's a sort of pitfall that we have to be wary of. Nevertheless, this is an awesome experiment. It's really very impressive. And it shows that 30 picoseconds is possible. So apparently we don't need to worry about positron annihilation physics at that point. Apparently, that has never been proven actually, that two gamma photons are emitted to within 30 picoseconds from one another. This now appears to be at least the case. So that means that at least from that point of view, there is some hope that we will still reach 10 picoseconds at some point. But they indicated the issue. There is no point in going faster and faster if it goes at the expense of other important parameters. And therefore, faster is not always a way forward. You can also play on other parameters in this equation. And a thing that has happened in this region, in California at UC Davis, is Simon Cherry and co-workers started working on this factor, the geometry factor, in collaboration with a Chinese company actually, who built this device. It's a PET scanner that is simply 2 meters long. So the patient is completely encapsulated in detectors and the radiation has no way to go. It will always be detected. And that leads to images like this, which is pretty awesome, right? It's a total body image taken in one time without any translation of the patient. We're now realizing that this enables whole new ways of doing PET imaging, like doing dynamic imaging with less than a second resolution either. You can inject the radioactivity and see it spread throughout the body, tells you all kinds of things on what is going on in there. These are very expensive machines, obviously, but they're fantastic tools to explore new things with. Its name is also the Explorer. But yeah, there's about 600 kilograms of scintillator in this system, and the scintillators are the most expensive part. So it's a very expensive machine, more than $10 million to purchase, mostly due to the crystals. So we want to see, can we make this a little bit more affordable maybe? And that brings me then to the other two factors in the equation. As I said, since this one goes in squares, it should never be forgotten. And if you can work on the cost of detectors, then having a lower cost per detector enables you to put more detectors into the system at the same cost. And that's a great way to improve efficiency as well, or sensitivity. And just very briefly, a concept that's now attracting a lot of attention. What you see here is a measured emission spectrum from BGO, bismuth germanate, which is a crystal that used to be used in PET a long time ago. It's a very cheap material, but the scintillation signal is not so fast as the crystals that we use today. So everybody thought this is not a good time, a flight scintillator, and everybody forgot about it. until we realized that it actually emits also some Cherenkov photons, which are not many of them, but they are quite instantaneous. This is a zoom. So we thought with this modern SIPM technology, maybe we can do the time stamping on the Cherenkov signal. And that appears to work. It does come with funny timing spectra. These tend to be Gaussian. Clearly, this is not a Gaussian anymore. And that is because sometimes you're triggering in one detector on a Cherenkov photon and on a scintillation photon in the other, and vice versa, and you get all kinds of mixes. So your timing spectrum looks a bit more complicated. But a large part of it is compatible with time-of-flight imaging in a very cheap material. And these are old results that we published in 2017, and I think there's one or two handful of groups working on this topic now, and people are already getting much better results. So I'm very happy to see this forward. And there are also other hybrid schemes people are working on in order to reduce cost, but still have reasonable time of flight. How am I time-wise? I have until the full hour, right?
Yeah, full hour, yeah.
Yeah, maybe, because I wanted to say a few things about time resolution theory, but that's complicated stuff, so I could switch to photon-counting CT also, maybe that's more interesting, yeah. Let me then just quickly change slides, because also, the slide format is newer, as you can say. This is more recent work. If you want to summarize what I just showed you in a few words, it is that the combination of scintillators and SIPMs is great for fast timing applications, whether that is time of flight PET or anything else. And so recently we thought, why not put the bar a bit higher and see if we can use that same combination of ingredients to solve an even more challenging problem. Also because the industry has absorbed a lot of what we have developed in the field concerning time-of-flight detection technologies. And for us as academics, it's also time to take the next challenge. And one of the new revolutions that is taking place today in medical imaging is the transition from conventional energy integrating CT to so-called photon-counting CT. In any conventional CT scanner works just like a radiograph. You're basically sending a stream of X-ray photons through the patient and measuring how much of that arrives at the detector. And you're considering literally the X-ray photon stream as a continuous fluence, and you're just measuring the attenuation of that. What if we could count every individual X-ray photon and determine its energy? You suddenly have a lot more information and should lead to much better image quality, as well as the possibility to measure some properties of the tissues you're imaging. So you can actually do material decomposition. And this is indeed becoming possible today. And this is an image that was taken in the Rotterdam hospital. That's pretty close to where I work in Delft. And you can see this is what they did. You can very easily recognize which tissue is which and make beautiful images like this. This is the result of decades of research in semiconductor detectors, notably cadmium telluride detectors. And the conventional wisdom was always that it would not be possible to develop such a system with scintillators because scintillators are too slow for that. And I think this statement is completely true, except for one wording. So that's our new mission, to show that you can actually do it with scintillators as well, if you combine them with SIPMs. So again, what is the task? You count the number of photons on every pixel in the detector, and you assign them to an energy bin. You may typically use 2 energy bins or 4 energy bins. The number is not very large. And of course, some of the important requirements is that you need to absorb X-rays up to about 150 keV efficiently. And the most challenging problem here is that you're dealing with pilot, meaning multiple pulses piling up on top of each other, because the photon fluence rate is phenomenal in this application. It may be necessary to count more than 10 to the 8th X-ray photons per second per square millimeter. So that's an enormous amount of pulses you have to deal with. So you need very, very fast detectors to avoid this pileup effect. The problem with pileup is that it leads to nonlinear distortion of both your photon count and your energy measurement. In other words, it deteriorates your image in a way that is also not easy to repair. Going back to what is actually a silicon photomultiplier based silicon scintillation detector, it's basically an array of crystals, one-to-one coupled to an array of silicon detectors, which means that what your pulses look like is the convolution of your scintillation pulses, which may look like this. So you have this exponential probability density function, but in every event you're basically sampling it with a relatively low number of photons. So you get this grainy look in every event. Then there is the response of the SIPM, which is typically also exponential. And the important parameter here is the so-called recharge time of the SIPM. And that's where it gets interesting, because the net result, of course, is the convolution of these two functions. And this is what a typical pulse may look like. Now, there are scintillators with decay times in the order of a few nanoseconds, and since a few years there are also SIPMs with recharge times in the order of a few nanoseconds. So then this pulse gets a width in the order of nanoseconds, and you may think of counting very high rates. There's another advantage, which is that in semiconductor detectors, you typically produce some 10 to the second or so electron hole pairs per event. And you need quite elaborate processing in order to deal with that, low noise electronics and so forth. Whereas in a scintillation-based system, because of the internal gain of the SIPM, you may have up to 10 to the 6th electrons per X-ray. So that's a much more comfortable system to work with. And you can do it with a very simple transimpedance amplifier, for example, maybe with a bit of low-pass filtering integrated, and you will have a very nice pulse. That's precisely what we did with very simple single pixel setups in our lab. Don't want to tire you too much with all the details of that, but one important number to remind is that we used SIPM prototypes with a recharge time, less than about 10 nanoseconds. So we built simple detectors like this, and did some count rate measurements with that using X-ray sources as well as strong isotopic sources. Simple readouts, transimpedance amplifier and digital oscilloscope, and limited offline post-processing, basically just some filtering. And then this is the type of pulses that you get. So in blue, some of the raw pulses, and as you can see, they're very strong pulses, easily in the order of 100 millivolts. And then the yellow and red curves are slightly filtered versions of the same signal. And you can see these are beautiful pulses. And so these should be very easy to process. With beautiful, I mean SNR is excellent. And using this, we were able to show that with lens and bromide scintillator, for example, we are able to count up to 20 million counts per second per pixel. And if you put then 10 of these pixels in a cubic millimeter, corresponding to a spatial resolution in the order of 300 microns, which is precisely what you want in CT imaging, you would be able to count up to 100 megacounts per pixel as desired. So then if you compare the numbers that we got with different scintillators, lens and bromide giving you the best numbers, to what is typically published for cadmium telluride detectors, we're getting pretty close to that with these materials. And to give you a sneak preview on even more recent results, this is a paper that has just been published with a new scintillator, It's a totally new class of materials. It's sometimes called perovskites. In essence, they are hybrid materials, partly inorganic, partly organic, arranged in 1D or 2D self-organizing patterns. We don't understand much about these materials yet. Many of these materials have been developed for photovoltaic applications or LED lighting applications. Some of them appear to be very good scintillators. This one, for example, has a 4 nanosecond decay time, which is quite spectacular, combined with a pretty good light output of more than 3 photons per keV. So that should be able to get you to a count rate capability that actually exceeds that of some of the semiconductor detectors. A lot of work to be done here. That looks very promising. So I think we have a nice challenge for the next decade to work on. Thank you very much. Yes. Yeah. Any questions? Or was I crystal clear?
Do you have any estimate of a figure of merit for the photon-counting CT problem? And if so, can you discuss what drawbacks you're trading off for with these scintillators?
Excellent question. Just thinking, I started playing with SR PMs in 2008. Back then it was a controversial idea. I think I came up with this figure of merit in 2018, so it takes about 10 years to come to the point where you can summarize things in such a simple equation. I started with this topic much more recently, so maybe I need a little bit more time before I start making very firm statements. We're really still trying to understand here how detector performance correlates to image performance. There's quite a few steps in between. There's the inverse reconstruction of the image from the projection data and so forth. So this is very nonlinear. One thing is perfectly clear, which is that again, the ratio of the light yield and the decay time of the scintillator is a good metric to say something about the quality of the pulses that you will get. Quality meaning the SNR of the pulses. And that actually correlates to what we've done for time of flight PET, although in that case also the rise time can be of importance. So that's one thing to look at. Another one is what I would call, we need a metric for the spectral performance. We used to use energy resolution as a metric for that, but I think it's a bit of a fault metric in the context of photon-counting CT in general, because of all these nonlinear distortions that occur due to pilot. To fully explain this would take too long, but to put it in simple words, a photon-counting CT scanner doesn't really measure energy, it just puts photons into 2, 3, or 4 energy bins. So it's more of a classification problem. So I think that a good metric for that is also one that's based on classification. And so we've proposed something like just measure which fraction of your photons are actually assigned to the right bin as a simple performance metric. So that's another thing you would need to look at. Then again, you need to stop all the X-rays. So you need to think about the cross-section for X-rays. Again, the material should be as cheap as possible. Has to be stable, meaning that if you put it in a machine and let it run for 10 years, there should not be too much radiation damage effects or other sources of material instability. You have to be able to produce the scintillator in a finely pixelated array, which in itself can be a cost factor. the machining, for example, of crystals. So if you can come up with the synthesis methods that facilitates making finely pixelated arrays, that would be a great advantage. It's probably more than that, but that's just some initial thoughts on what would make for a good detector. I don't expect a lot of, I mean, I'm talking really about the scintillator here because I don't foresee many problems on the SIPM side. You would, of course, also need finely pixelated SIPMs, but that is a fairly straightforward thing to do once there's a market for it. And that's just different lithography mask, basically. And you don't need to change much in the SIPM technology itself. It's just a different layout. So that technology is really there now. And of course, you can refine it. But I think the real challenge here is to find the right scintillator. The rest the industry can do.
Other questions?
I think you mentioned that having photon-counting screens will provide you with more information than the traditional energy-based CCTs. Do you think it also allows more opportunities to be compatible with like multi-modality images and have CT?
Well, to be honest, my primary motivation to think about this is that I'm also involved in some radiotherapy research, where people want to be able to move to image the patient while the patient is in treatment position. And that is, you get the best images with a conventional fan beam CT, so a donut, but that's not very easy to integrate with a treatment gantry. So what people use in treatment gantries is so-called cone beam CT, where you have a large X-ray panel on one side and an X-ray source on the other side. So if you could bring photon counting capability to these large panels, that would make it possible to do this sort of thing in a radiotherapy gantry. But then the cost becomes a really important factor, because in a fan beam CT you only have one row of detectors in principle, whereas now you have a full panel which might measure 30 by 40 centimeters, for example. So that greatly increases the cost, and we need more cost-effective solutions. And for example, this perovskite material I've been showing you is a material that you can synthesize in liquid, in water actually, at low temperatures, and it appears to be a very cost-effective process. And as the price of SRPMs is also going down, still going down, so hopefully we'll be able to make a very cost-effective imaging technology in this way that will make this sort of thing feasible.
Well, the students will get another hour to talk with Dennis and ask questions about his research, but also his career path and things in Delft and Europe. So for now, let's thank our speaker again.